Yeah, so I'm gonna talk about it. So there's something I want to show you probably after I finish the section on RC circuits, probably before the break, is something about topology in circuits, because you guys were asking me, right, what was the application of topology in physics besides quantum mechanics. So my previous answer was based on my own research field, which is in gravity, but in circuits also, in the things that we're talking about, is also having some kind of topology. So I'm going to explain to you about it, and I will share with you a paper that a friend of mine written, and the story of how he got the idea and how he wrote the paper is also kind of interesting. So I'm going to tell you about that later. But I guess for now, let us finish off the topic about the last topic of chapter 4. So chapter 4, we have been talking about circuits, right? And we have been learning how to use the formula for series, resistance in series, resistance in parallel, and then in the more complicated problems, it is better to use the Kirchhoff rules, right? And we have been using Kirchhoff rule in a few examples in the previous class. And right now, what we're going to do is we are going to put a capacitor into the circuit now. Okay, so if we put a capacitor in a circuit, then the current will no longer be a constant. So that is one main difference of this part compared to the previous part. So previous part, right, everything is resistor. You attach it to a battery, you turn on the current, right? You turn on the switch, and then the current will flow. The current will flow in a steady state. That means the current is constant for the resistor circuits. Okay, then we just calculate resistor and things like that. So that is one situation. So this situation, right, the current cannot be constant because there's a capacitor. So why the current cannot be constant in the capacitor? Because basically, right, the main reason is capacitor consists of a plate and then there's a gap in between. It's either a vacuum or you fill it with dielectric. Either way, the charges cannot jump over, right? So that is the main issue over here. So there's two parts, right? So there's two parts to this section, which is charging a capacitor and discharging a capacitor. In both cases, the current is not a constant. Okay, so to see what's going on, let me draw the circuit. Okay, so the circuit goes like this, right? So I have a resistor, and then I have a capacitor. Okay, so the resistor is having resistance R, and then the capacitor is C. Right, so the resistor is just representing some resistance in the circuit. You can say it's a resistor with ideal wires, or if you just attach a battery to an actual capacitor, right, the wire itself has some kind of, if you do not neglect its resistance, it's going to have some kind of resistance. So there's going to be some resistance anyway, right? If it's not the ideal case. So if so this is a capacitor. We have learned about capacitor, right? If you attach it to a potential difference, it's going to charge up the capacitor, because the positive terminal, we can treat it as a source of positive charges. So the plate will accumulate positive charge on this side, and it will accumulate negative charge on the other side. And once it has been fully charged, the current stops flowing. That depends on the capacitance. If it has a high capacitance, right, Q over V, then it can store more charge. So it can store until the until the maximum amount of charge. So once it reaches the maximum amount of charge, once it fills up with all the positive charges and negative charges, the current will stop flowing. But before it's filling up, during the time it's filling up, that is what we want to calculate, right? So we start with a blank capacitor. So what we have here is the capacitor. Our capacitor is initially uncharged. Okay, so that means I will use little q as the symbol to represent the charge, right? So it's a function of time. Normally I use big Q, right? So big Q for capacitor is the final charge. So we can be consistent here. So Q is equal to 0 at initial time 0, right? So I have a blank capacitor. If I attach this to the circuit, it will start to charge, right? So it will start to charge. That means if it's initially no charge, then all the current will flow, right? So the current will flow to start to fill up the plate here. So initially I have a lot of current, right? But as the plate start to accumulate positive charges, then is a positive charge, so it starts to become a repulsive force. So the current flow will start to reduce until it reaches the maximum charge of the capacitor. Then the current will eventually stop flowing. Okay, so that is the situation that we want to solve over here, right? So what we have here is there's a EMF source, so I have a epsilon, right? And then I have the potential difference for the resistor, and then I have a potential difference across the capacitor. So from here I can use the Kirchhoff rule to solve the problem. So we are going to use the Kirchhoff loop rule. Did I press record? Has. Yes. Yes, I'm recording. Okay, so using the Kirchhoff loop rule, I go one round. So we do our usual thing probably by now, right? We choose one loop. There's only one way to go here. So we go one loop. The EMF source is a positive E, curly E, right? And then R and capacitor are the components that are not EMF sources. So they are, what we do is we minus, right? So the current, we will take the current to be flowing this way. I will use the little I to represent current because the current is not constant. Okay, so I minus the potential difference across the resistor minus potential difference across the capacitor. It should become 0. And the EMF is equals to, well, VR, right? So VR is I, Ohm's law, IR. And then the potential difference for CV, for capacitor is the formula Q over C, right? So if you remember, hang on, I forgot my black. So if you remember your potential difference for capacitor, right, we have Q is equals to CV. So when my charge is, at the moment when charge is Q, the capacitance is C, and then the VC is given by this. So VC is just the charge at that moment divided by the potential. So V is minus Q over C. Okay, is equals to 0. So in this situation, right, the I is not a constant, it's a function of time. Like as I was trying to convince you, the instant you plug in the capacitor, the current will flow as fast as it can, but as it fills up the plate, it will reduce. So it's a function of time. The charge is also a function of time because initially it's 0 and then you start to increase the charge. Okay, so that is the equation that we start off over here. So this will become a differential equation, right? And right now you guys are taking the ODE with Taoshan, right? So this is actually I is the rate of change of current, right? So this will become an ODE, and we will solve this like any other ODE kind of system. Okay, but it will become a simple ODE lah. So we have not used the full power of Taoshan's course yet, but that will come later. Okay, but in any case, I have I is equals to dq dt R, right? So remember the definition of current is equals to 0. So this is a function that we can try to solve, right? So I want to find what is the charge as a function of time. Okay, so at time 0 I know it's 0, but at some later time how does it change? So we just rearrange this a little bit. So I got R dq dt, right? So I move this to the positive side, then I got curly E minus Q over C. So looks like I can rearrange things a little bit. dq dt is equals to E over R, right? So it's the EMF over the resistance of this R, and then I divide by Q over RC. So this is a Q variable. So what I can probably do is I can do this, right? So I can do this. Yeah, so I got E over R minus Q over RC, and then dt. But it looks like it's a bit ugly now. So yeah, like what we said last time, right? Mathematical aesthetics. I want to make things look nice, so I take out Q over RC. So this becomes ER and then minus Q dt, so that my RC comes to the top, right? So RC comes to the top, and then I want to bring over to the right hand side. So I got dq over E minus ER. Yeah, it's the morning, so we don't function well in the morning, right? So this is one of the problems, RC, right? So we got this situation over here, and then we want to integrate both sides. So we want to integrate both sides. So let me write a new line so that it looks nicer. ER minus Q is the integral of dt RC. Okay, so this is the this is technically an ordinary differential equation, but it's first order. So I think you learned this in the ODE course, right? If it's separable, this is a separable ODE. So if it's separate ODE means I can push everything to one side and push everything to the other side, and then I integrate both sides, right? So what is the limits of integration? As I said, we know that our capacitor is initially uncharged. So at time 0, my charge is 0. I just want to integrate until some later time t, it will get some final charge qt, right? So just perform this integration. This is pretty straightforward to integrate. I got negative logarithm of ER minus Q from 0 to some later Q. This integrate becomes Q over RC. So I got the log of ER minus Q over ER is equal to minus T over RC. So from here I can get well, ER minus Q is equals to ER e to the power of T over RC, right? And then rearrange a bit further. I will want to find Q, so I'm finding Q. So I bring Q to the positive side, and then I bring this over, so I got ER, and then I got 1 minus exponential of T over RC. So I have finally found my function of Q. So this is how the charge changes on the capacitor over time, right? So this is the equation for Q over here, right? So this is an equation for the capacitor charge during the process of charging. So yeah, denominator on the left. Did I forget something? This one, is it? Oh, EC, yeah, I meant to be EC. Correct, yes, you're right. I pull out a factor of 1 over RC, so this becomes a C. So this becomes a C. This becomes C. So everybody here becomes a C. Let me start a new line. Okay, so let me check the notes. Yeah, it's correct, it's correct. So what we have here is yeah, let's do again, right? So it's minus the logarithm of E capacitance minus Q from 0 to Q over T over RC. So this is the logarithm of EC minus Q over EC is equal to negative T over RC. And then take the exponential of both sides is equal to EC e to the power T over RC. And then I bring Q to be positive, so I found Q as a function of time, so it's EMF capacitance 1 minus e to the power of T over RC. Okay, so yes, thanks. Now is correct. Okay, so this is now my page 2. Okay, yeah, so this is how the charge changes over time, and we can easily plot the graph. So if you look at the graph, right, at time 0, e to the power 0 is 0, so initially I have 0 charge. But this is an exponential graph, so as time goes on to infinity, this will become approaching to EC. So this is something like Q is equals to CV. In the previous chapter, we call this the potential difference across the capacitor, right? And that is the potential, the voltage of the battery. So this is the V that we're talking about, right? So if you see the graph, it's going to look like this. So this is how it changes over time, right? So the charge on the capacitor is asymptotic to EMF times the capacitance, right? And then it is a 1 minus exponential graph. At time 0, the charge is 0, and then I will increase. So it's an exponential increase, but asymptotically approaches to this line. Okay, so this is what we call the final charge of the capacitor, right? So this is the line where Q is equal to EC, the full charge of the capacitor. So this is the charge when the capacitor is fully charged, although as you can see mathematically it never exactly reaches this point, but it's getting closer and closer. So most of the time, yeah, within seconds we will reach close to this value, and in terms of measurement wise we can't even tell the difference, right? The difference is so small. Okay, and we are using our idealized equations anyway. So that is our charge of the capacitor. So now we know, so not only we know how to calculate the final charge of the capacitor, now we know the details, right? Between a blank capacitor and then the moment you plug it in, how does the charge increase? Okay, so this depends on T over RC. So I'm going to talk about T over RC in a minute later, but we notice that this RC, we will call this the time constant of the capacitor. So it depends on R times C. So if RC is a small number, right? If RC is a small number, then the exponential, it will increase at a faster rate. So if the circuit has a low resistance, it will reach the maximum charge faster. If the circuit has a high resistance, it will become slower. So it depends on the situation. And I believe for most real life circuits, you can almost reach here within a few milliseconds. Right, so this graph is like should be around the order of milliseconds. So things go very fast for circuits. So that is for the charge, right? How about the current? So what's the current passing through the circuit? So the current is the rate of change of charge. So current I, right? Well, I can also determine the current as a function of t. It is dq dt. So if I differentiate this with respect to time, then the first term is 0, then I got negative and then minus 1 over RC, and then e to the power t over RC. Okay, so these two terms will cancel, right? So my current function is just EMF over the resistance, e to the power of minus t over RC. Okay, so at time 0, the current is EMF over R. So at time 0, the current is just like Ohm's law between these two. So because the capacitor has 0 charge, so it's like kind of like not really affecting the circuit yet, but as it goes beyond 0, the current will decrease, right? So this is an exponential decay. So if I plot the graph of current against time, current, so this is the charge against time, then initially this is the EMF over the resistor, but this is an exponential decay. Okay, so as the charges fills up, the current will reduce, right? It depends on how much you fill up the capacitor. So once the capacitor is fully charged, then the current will become 0, so the current stops flowing. Okay, so that is what you get when you have a fully charged capacitor. Okay, so any questions so far? Yeah, still waking up. Me too, I'm still waking up. Okay, so that is charging the capacitor. So the next part of the story is discharging the capacitor. Okay, yep. Equation 4.2.1. Yes, correct. There's a negative sign missing. Yes. Thanks. Yeah, I'll fix it later. So I should put a negative sign because it is an exponential. Because it is an exponential decay, as you can see from the graph, right? Where are we? So over here, yes, this is an exponential decay. Oh, the previous one already got, yeah. So any other typo? Okay, so I think that, yeah, so that's it for the charging. That's how we charge a capacitor. But what happens if we discharge a capacitor? So it's kind of like the same story in reverse, but with a big difference. We do not have a battery, right? So yeah, so let's see how it works. Okay, so I have a capacitor at time 0. It is fully charged. Okay, so at time 0, the capacitor is initially having a charge Q0, right? And then when connected to a circuit with a resistor, it will discharge, right? So that is kind of like yeah, so this is what is happen if you attach a fully charged capacitor. So let's say my capacitor is having a capacitance C, right? And then I attach this to a resistor, so I have a resistor of resistance R. Okay, so R, and then what's going to happen? So the current will flow as usual, right? And I still use the Kirchhoff loop rule. Really? No lah. I use frac. Where got AB? Yeah, I use frac. So yeah, it is the same thing. So no package here, as you can see, right? The T over RC is still appearing as a T over RC here, right? But if I use the frac T, frac RC, it will appear as a proper fraction. So nothing special there. Yeah. I wish there. You can maybe define a shortcut command, but usually I think we cannot avoid typing frac. So yeah, yeah. But sometimes I do the command called half lah. Yeah, so half, you can define a command called half, and then it will come out as a R over C. Yeah. So if I do half, did I define it here? I don't think I did. Yeah. So half will come out here. So you can do half or a quarter or things like that. So the fractions that appear quite often, you can just define a custom command. Okay, so yeah, so let's use the Kirchhoff loop rule. Right now, I've only have two things, right? So the potential difference across the capacitor and the potential drop across the resistor is equal to 0. And this one across the capacitor is Q over C. So I'm still writing small q because it is going to be a function of T. The minute I connect this, the charge will change, right? And it will decrease, as we can see here. Fully charged, but it will start to flow and it will neutralize with the other plate. What about the resistor? So it is the current, right? So it's the current I, R, and then this is equal to 0. So yeah, so let us rearrange this. So I got IR. So IR is equal to minus Q over C. I will bring R to one side, so I Q over RC. And we remember that the current is the rate of change of charge flow. So I is equal to dq dt. So dq dt is Q over RC, right? And then I bring this down. So dq over Q is equal to minus dt over RC. So RC is a constant because they are just the same components throughout the entire time. And we can now integrate both sides of the equation. Okay, so according to what we know, initially at time 0, the charge is Q0. So at time 0, my initial charge is Q0, and then until some later time t, I will have some later qt depending on what this is, right? So this is a function that we can easily integrate. This is a log q. The limit is from q0 to whatever qt over here, and integrate here is just t over the time constant. So what we have here is q over the initial charge, t over rc. So my q as a function of t is now q naught exponential t over rc, right? So this is my function of q. So at time 0, e to the power 0 is 1. So at time 0, the charge is initially q, but as time goes on, the charge will drop, right? So it is a exponential decay. So if you draw the graph, it is going to look like this. Okay, so how does it change over time? So this is the graph of q. So at time 0 is initially q0, it will be an exponential decay, like this. Okay, but what happens to the current, right? So current is the dq dt. So if I differentiate this, then I get minus q over rc e to the minus t over rc. So this is a negative exponential decay. So at time 0, I start from a negative region. As time increases, this magnitude will decrease, so it will become a smaller factor to multiply this until it approaches 0. So this is a graph in the negative region. Okay, so this is it, and then this is t. So I started out as minus q0 over rc, and then this is an exponential decay towards 0. Remember what we talked about when we get a negative current, right? When we get a negative current, is the direction that we guess is wrong. But this picture is symmetrical, so it doesn't really matter what's the current anyway, right? So that means the sign of this is the sign of the current that we assume was wrong, right? And why did we so the sign that we did is wrong. So what is actually happening here is q over c plus ir equals to 0. So if I bring both sides, right, so I got plus minus ir equals to 0. So this is where you can see that now the VC according to Kirchhoff's rule should be a positive number, and the potential drop across the resistor should be a negative number. So this is how you can, another way you can interpret this situation as the voltage drop for capacitor and R is opposite sign. So that means one is serving as an EMF source, the other is using up the electricity. Okay, so that is how we get our result of the negative current. Okay, so yeah, so we got the function of Q, and we got the function of I. So this is the discharging a capacitor. Any questions so far? Your brain blur. Not that blur, right? You can spot my typo and mistakes. So I think it's pretty good. You're on track so far. Right. But I think everyone else, I don't know, is a bit more quiet than normal. So I don't know what's happening with everyone else. Okay, so yeah, I haven't wake up yet. Yeah, so let's talk a little bit about the time constant, because both our solution, right, both cases we have the exponential curve, exponential function. So both cases involve this thing, right? So it's t over rc, right? So what we're going to do is we're going to define, I mentioned this a bit earlier already, is the time constant. Okay, so the time constant, and we call this the letter tau is equal to rc, right? So that means this becomes e to the t over the letter tau. Okay, so the handwriting must be precise. This is a Greek letter tau, this is the letter t. Okay, so these two different symbols, but the how fast the current decays will depend on the size of this constant T, right? So for example, if I'm having a discharging capacitor, right, then my Q of T, the result that we got just now was, charging. So when I'm charging, it is EMF times capacitor, and then 1 minus e to the decay, right? So T over tau. And then if I have a discharging, then my current depends on my initial value and then T over tau. So if I draw the picture of discharging, right, so let's draw this picture, this example over here. If I draw the picture of discharging, then if my tau is a large number, then is this, so this is T large, the tau large. But if I'm discharging with a small time constant, then this is small tau. Okay, so it will tell you how much does the capacitor decay. Okay, so that is just the time constant, right? It's just a constant to tell you what is RC, just to see how the circuit decays. So that is about it. Yeah. Well, everyone's half dead. Okay, so yeah, enjoy your breakfast. I haven't eaten mine, but I'm not hungry, so but in any case, yeah, so that's it for chapter 4, right? So this is the last thing that we want to discuss about chapter 4 is to charging and discharging capacitor. So this is one example where the current is not a constant. We will come back to this type of similar problems later when we start to deal with AC circuits. So AC circuit, we are going to deal with a capacitor and a resistor and then an inductor, right? We haven't learned that yet. That is where we really need to solve a second order differential equation, right? So what we are solving here is first order. And I believe Tao Chan's course, I'm sure he got he did mention he got some examples involving the LRC circuit, right? So maybe you have already solved something similar. So I don't know, maybe we'll come back to this again. In any case, we have kind of mostly finished the main chunk of section 4. What time are we at now? So we are, yeah, so we still have plenty of time. Let's go to the next chapter about magnetism, right? So we will talk a bit about magnetism and then we will take a break, and in the second hour of today's class we will do some tutorial questions about the tutorial 3 questions, right? So we still haven't finished the second half tutorial 3, so we'll do that after the break. But for now, let us talk about magnets. Okay, so chapter 5, magnetic fields. Okay, so this is where things start to kick off, right? Like I was saying on Monday, chapter 1 to 4, relearning things from, you probably learned from high school, but right now we are learning magnetic fields, which is a bit more complicated. And the reason why it's more complicated, right, is, well, it has a few issues related to magnets. Charges and electric fields are straightforward. Magnetic field, right, generally you feel like things like, you know, if you use calculus formula, you see curl, and then you see things going in circles and things like that, and that in that sense is kind of like the rotation version of mechanics, right? So remember when we are doing mechanics, the first 4 chapters is Newton's law, everything going in a straight line, and then we go to rotational chapter, it becomes complicated. Magnet has things going round and round and round in circles, so that is where it is kind of like complicated in that same way as well. Okay, but what's a magnet? If you look, magnets that everyone knows, right? Even for those who don't know physics, is something with two sides, which has a north pole and a south pole, right? So magnet has a and south pole. Okay, so it creates a magnetic field. So famously, magnets were discovered in Greece, I think, right? And yeah, the word come from something magnesia, something. I don't remember the details, but we can easily find the Wikipedia for it. But it has a north pole and south pole, and of course, since the olden days, right, people have been using magnet to become a compass. Okay, and that's why we call it a north pole and a south pole, because every magnet has two sides, right? So one of the side will point towards the north, and the other side will point towards the south. Okay, so imagine, right, when it was being discovered last time, it's kind of pretty amazing, right? I have some kind of material that can automatically point to the north and point to the south. Okay, so and now we understand why. It's because of the magnetic field. Our Earth itself is one huge magnet, and therefore that is the reason why the magnets work in that way. Okay, so a magnet has a north and south pole. So usually the magnet kids get to play around is a bar magnet. So it has a north pole and has a south pole, right? And then we have a magnetic field. So the magnetic field around a north pole and south pole probably looks like this, right? So going here, and then so it's a loop from north to south, right? And then yeah, so it keeps on going forever, and same thing for the other side. My drawing is very ugly. Okay, so like this, like this, like this, right on the symmetry line, like this. Okay, so this is my magnet. Okay, so this is a new type of field. So it's no longer electric field, it is another vector field. So we are going to call the magnetic field B. Okay, so that is a common notation for magnetic field. Notice that if I draw the magnetic field around the bar magnet, right, it is similar to electric dipoles. Okay, because remember, how does a dipole look like? So I have a positive and negative charge, right? And then I have a field coming this way, and then a field coming this way, right? And then you have loops, right? And then like this, and then like this, like this, and then like this. Okay, so it has some similarities, but they are not the same. Okay, so they are not the same. You can easily show that they are not the same thing because the E field cannot superpose with the B field. Right, B field is a separate thing, right? So they are like kind of independent of each other. Okay, so that is the similarity. How else are they similar? So for magnetic field, we call them north and south pole. For electric fields, we have positive and negative charge. So they behave in the same way. So for example, the same poles, they repel, and then opposite poles attract, right? So for example, right, if I take the same pole, so south pole, if I put the south pole next to each other, the two bar magnet will repel each other away, so the force will be opposite. Okay, so if even if you flip, you do the same thing. North with north also will repel. Okay, so they will repel. But if you put the same poles together, north to south, but next to the north to south here, this is a attractive force, right? So same story here. If I flip north next to south, it will be still attracting, right? So the same is also similar to dipoles. Dipole, if I put positive negative and then negative positive, this will repel each other. But if I put the positive negative and then positive negative here, this will be attracting each other, right? So it is the main reason for electric field. We understand this already, right? So this is Coulomb's law, right? So the reason why this is happening for electric field is Coulomb's law. What we are going to do over the next few chapters is to understand this side of the picture. And it is a bit more complicated already, because we will not learn the version of Coulomb's law yet, right? Not yet. Okay, so but we will slowly reach to that point. Okay, so that is how the magnets work. Yes, powers of magneto. Okay, so you guys are talking about the yeah, because Professor X, we have two possible Professor X, right? Darren and Xiongsi. So let me get some paper. Yeah. So yeah, I think physics students haven't met Professor Darren yet. He's from the MAT department, so MAT students know him well, right? He hasn't taught, unless you took one of his game theory GEs. So so that is the similarities of magnets with electric field. But what are the differences? Okay, so that is the main thing. The differences is actually a huge problem. Okay, so differences is how to say, there's no magnetic monopole. So but I try to put it in a simpler English before we use more advanced words, is that the north and south poles cannot be isolated. Okay, kind of, or yeah, this isolated means separated lah. So that is yeah, so if you're having any interest in physics research, right, this is one of the biggest unsolved problem in physics. If I take a magnet, right, this one is a biggest unsolved problem, but everyone can understand this problem because we can try this at home, right? We can kind of buy a magnet from a shop, right, north and south magnet, and we can try to cut this, right? So if we cut this, what we end up here is we are just ending up with two north-south and north-south. Okay, so we cannot separate a north pole by itself, and we cannot separate a south pole by itself. So you cannot get something that is only a north pole and that is something that is only a south pole. So you cannot, this thing cannot happen. So even if you cut a magnet, you just end up with north-south, north-south, right? And that is the reason why we say that we have no magnetic monopoles. Magnetic monopole is another way of saying magnetic charges. Okay, of course, right, if you're talking about electric field, we have been dealing with isolated charges all the time, right? So we have positive charge and then negative charge, no problem, right? So electric field, no problem, but for magnetic field, we cannot, right? And yes, so that is why we cannot, that is one of the biggest unsolved problem in physics. So why is it an unsolved problem? Well, it came from the theory of electromagnetism, right? So by today, all the physicists understand electromagnetism very well. We understand the theory from the most abstract mathematical foundations to all the experiments. And all the theory that we have so far, right, none of them have a law that says that there is no magnetic monopoles, right? So there's no law that says no magnetic monopoles. There's no theorem that will disprove the existence of monopoles. And the experiments that we can do is, well, even experiments say that the best the experiment can do is no monopole has been discovered yet, right? It just said that it's just not around here. Maybe there is one somewhere in another galaxy, in another universe, but we just can't find it, right? So this is one of the still open mystery of the universe. And if you dig deeper and deeper into the theory, like all the theory says monopole can exist. This is also another application of topology. Was it Kaheng who asked about topology, or Eric? If you use topology, right? If you apply topology to Maxwell's equation, the law that says no monopoles, there's actually a loophole. There's actually a gap, and there's a way to say, oh, actually, because of topology, you can say that there exists a magnetic monopole. So that is the problem of the Dirac string and the gauge invariance. If you heard these words before, if not, never mind. We will slowly reach that level over the next few years, right? So it is one of the big problems in physics. And yeah, so if you happen to find one, make sure you keep it, because you will win a Nobel Prize if you found a magnetic monopole. Okay, so yeah. What's this? 1 million is soft. Yeah, Nobel Prize, the Nobel Prize money is $1 million, right? Or 1 million in the euro, so you convert to RM or whatever. But yeah, so it's one of the biggest unsolved problems in physics that we have so far. There's another differences. Well, this is kind of the obvious thing. Magnets can attract non-magnets. Usually, if it contains iron, right? So if I have a magnet, right? So if I have a magnet, okay, so north, south, right? So let's say I have some metal thing, so yeah, metal nail. It will attract, and if we are talking about non-magnets, right, the direction of is always attractive, even if you flip the north and south. Okay, so if I take a paper thing, it will still be attract. So this one is something everyone can experience, right? Because I can even do this with my headphones, right? So headphones can attract. Yeah, it can attract your paper clip, and it doesn't matter whether you are north or south pole. It will still attract, right? So, and then also, once you attract, of course, another thing you realize that if this is attached to a magnet, it turns out that this new object itself, now it becomes a magnet because it itself can start to attract other things, right? So you can make a chain of magnetic material. I'm surprised that I can even do this with headphones, because headphones should be quite weak, right? So you can do this. You can make you can see how long you can go, right? So this is the process of magnetization. So yeah, so that is how magnets work. And the reason how it works is you'll learn this a bit more in your future courses. It's non-magnet, but this thing, if it contains iron, right, the atoms behave as tiny little magnets. Okay, the reason why they are not magnets right now is that the magnets are all in random direction, so the magnetic field cancel each other out. But if you attach this to a magnet, right, if you attach this to a magnet, it will pull all the south poles of the atoms in one direction and all the north pole in the same direction. So it becomes magnetized, right? So it will turn a non-magnet into a magnet, and then yeah, then it can start to behave as a magnet itself as well. Okay, so that is another thing how magnets work, and it is indeed a different property from electric fields, because you can't really do that with electric field. Maybe if you use something, yeah, maybe static electricity, you can do a similar experiment. If you rub a cloth, something similar happens through there as well, right? So that is the fun thing that you can play around with when it comes to magnet. Okay, so it's good that you wonder what is a magnetic field and how do we produce it, because we are going to spend 2-3 chapters to understand how it's being produced. So yeah. Okay, so that is one issue about magnets, right? So actually I'm only talking about magnets, and so Yiming's question is good timing, because now we start to talk about magnetic fields. Okay, so the thing about magnetic fields, right? Okay, let's start with this issue. The issue about no monopoles. Okay, so what is the consequence of having no monopoles? For electric fields, right? Electric field, we have charges, so no monopoles, no magnetic charges. Magnetic charges. For electric fields, the magnetic charges are the starting and end points of E, okay, of electric field lines. Yeah, this is just to, I'm just repeating what we know about electric field, then later we contrast what happened to magnetic field. So remember, right, if I have a positive charge, it is a source of electric field. So electric field comes out of positive charges, right? And if I have a negative charge, then the electric field comes into the negative charge. So the line starts from positive charges and it terminates on negative charges. Okay, so that is what happens when we talk about electric fields. So these are electric fields. Okay, so these are the starting and end points. So because we have no magnetic charges, not to say we have no, just that, you know, theory and experiment, theory says yeah, it can exist, but just the experiment, we just cannot find it, right? So since we don't have magnetic charges, and I should say yet, right, just in case somebody finds one and wins the Nobel Prize, then my video is not outdated, right? So since we don't have magnetic charges yet, then my electric field lines do not have starting or end points, right? So if it charges, the fields, they terminate somewhere or they start somewhere and go off. So but magnetic field do not have, right? So that means the best we can do is the magnetic field, the consequence here is that they exist in loops. So if they exist in loops, they don't need to start, they don't need to end, they just go around and around, right? So that's why you got magnetic field that is going in circles, right? So for example, you have this type of situation, or for the bar magnet, right? Remember what we draw for the bar magnet. So the bar magnet is let's say north and south. So for the bar magnet, my electric field is just go outside, go one round and then come back, so it closes in a loop, right? So same thing for the other direction. Okay, so it closes in a loop, right? So the north and south pole is behaving similar to dipole, but there's actually no magnetic charge here anywhere inside the bar magnet. So what is happening is the magnetic field just pass right through and continuous. So everything goes in the loop, right? So that is our that is the main property of magnetic field, and that is kind of the reason why magnetic field is a bit harder to calculate, because everything is circular. And as we have learned since the previous course, right, circular motion harder to solve, right? Linear mechanics easy to solve, like rotation very hard to solve. So that is the main reason. So that is the introduction of our magnetic field. And one more thing to introduce is the SI unit for magnetic field. We have the Tesla and also the Gauss, right? So what was the Gauss? The Gauss and then we have the Gauss G, and they are related to 1 Gauss is 10 to the minus 4 Tesla, or was it the other way around? Let me just double check, because it is the morning, so I tend to make mistakes. Yeah, so 1 Gauss is 10 to the 4 Tesla. Okay, so that is the magnetic field. What is a field in physics? In physics, basically a field is a function. It's a function of so yeah, so just to answer your question, right, because this is a good question actually, because in physics we deal with a field all the time. A field is basically a physical quantity that depends on position, right? So x, y, z, right? So that's why electric field. So magnetic field, right? It means that every point, if I say my coordinate x, y, then if I specify a point, I can get the field. So same thing for electric field, right? So electric field, we have talked about the electric field, right? And then we have talked about magnetic field. In previous courses, we talked about gravitational field. So it's a fancy word, but it just depends on what topic we are studying, right? So yeah, so maybe you feel confused if we say field all the time, but if you're talking about this chapter, it's magnet, right? So we draw the vector for magnetic field. In the previous chapter is the vector for electric field. In the other chapter is the gravitational field. Okay, so yeah, it has been 1 hour already, so we probably should take a break. I just need to talk about one more thing about magnetic field. So after the break, we will talk about one more thing, and then we will do the tutorial questions. Okay, so yeah, so let's stop the recording here. Yeah, so everyone had your breakfast already? Everyone is back, right? Then let's continue our discussion. Oh, yeah, you can see, yeah, Zuru, you can see most of them in the chat. I was just telling everyone about what is quantum field theory about, and whether anyone is interested in string theory. So that is kind of, yeah, so actually, in fact, yeah, let me know if I have enough people interested in string theory, then I will try to arrange something with my string theorist colleague in Singapore and ask him to give a public talk or something. Yeah, so you guys think it's cool, right? Yeah, maybe I will do a poll somewhere. Then yeah, so I can do a poll based on who I can invite, and then I can arrange some topics and then invite who is the based on the interest that you guys have. Yeah, so it will be a counter to, because like the Wednesday seminar, you guys are saying it is experimental based, and it is true, right? Most of it is based on, I mean, a lot of physics is actually what is discussed in the Wednesday talks is like experiment, condensed matter, things, that kind of thing, right? But if you feel if you want to hear about other things, I can try to arrange something. Because yeah, giving talks myself, I can talk about the same few topics all the time, right? So I can try to drag some people over. See, yeah, I will see how. But one last thing to talk about before we do tutorial is to talk about the magnetic flux. Okay, so let's finish this off and then we do tutorial. But don't worry if I can't finish all the questions. As always, I will upload. solutions. So magnetic flux is defined in the same way as electric flux. So instead of electric field, I have a magnetic field, and then you do the integral over the area vector. Okay, so that is basically about it. The SI unit for electric flux is, we call it 1 Weber. Okay, so 1 Weber is by SI unit, flux for B is Tesla, and then times the area. So 1 Weber is 1 Tesla meter square. Okay, so this one is called the Weber. I think it's named after another physicist, but in any case, we got so we got this now. And in relation to magnetic flux, right, I want to see what is the consequence of having no magnetic charges. So if I have no magnetic charges, right, all the magnetic field occur in the loops. Okay, so and then what is the consequence? So let me write this here, right? So magnetic field, so no magnetic charges. So the consequence of having no magnetic charges is magnetic field must exist in loops. So yeah, so this is also another reason why calculus 2 is important. We will see here, because it involves a surface integral. Magnetic field must exist in loop. The reason is because we have no magnetic monopoles. Right, or we call this charges. There is no charge for magnet, right? So what is the consequence, right? So remember, if I have a charge, right? If I had a charge for electric charge, right? So E dA, then this is the enclosed charge over epsilon. But right now, the problem is I have no charge for magnetic field, right? So what is happening here is that the flux over a closed surface of any closed surface must be exactly 0, because I have no charges for magnets. Okay, so the consequence from here is that the magnetic flux, any closed surface, must be 0. Okay, so this one, if it's not a closed surface, okay, fine, got some value. But if I do for entire closed surface, it must be 0. You can easily see over here, right? So the bar magnet is a closed surface, but you see that the amount of magnet that comes out is the same magnetic field that comes in. So the amount of magnetic field that comes out is the same magnetic field that comes in. So what goes out must come in, because the magnetic field lines exist in loops. So no matter what the shape, right, whatever vector that come out, it will come in again somewhere else. So no matter what the shape, right, it doesn't have to be a square or anything. And that is the interesting thing about the closed surface. So as long as there's no charges, so the flux through any closed surface is going to be 0, immediately 0 for magnetic field, because we have no magnetic charges, at least not yet, right? So yeah, we have been doing experiments for the past few hundred years. We have not found magnetic fields and magnetic charges, so therefore this equation, we shall treat this to be true at the moment. Okay, so that is the reason why, right? So the argument here is only because we have no magnetic charges. If we have a magnetic charges, we would have a law something like this, just that we don't have. Okay, so that is the main issue that we have about magnetic fields at the moment. Okay, so yeah, so that is the introduction to magnetic fields. We will continue the rest in next week, but we should probably do some tutorial question, right? So let's do some tutorial question. Let's pick up where we left off. We were at tutorial 3, right? So we did until, oh yeah, I haven't told you about this other friend. Well, his research is in condensed matter physics lah. So probably, yeah, don't drag him to talk to invite, right? Oh, you guys already did it. Okay, that's That's good. Major elective, you mean? No. String theory is yeah. So right now, 4 people say yes. Come to seminar anyway. 5 responses. Yeah. So I'm sure you guys have seen all the memes about Tesla, right? Somehow Tesla is very popular in the internet. Tesla versus who's the other guy? Yeah, I even forgot who's the other guy. Edison. Yeah, Edison. AC versus DC, things like that. And Tesla is in many movies, right? Yeah, I will make later. Yeah, so I will make later and do a list of different topics and see what you want. But no guarantee lah. If maybe the person is busy or something, then no choice, right? But at least I will try. Hopefully we can get lucky, and we can get some arrange some talk, because it's gonna depend on a lot of factors, whether yeah. So let's try. In any case, let's do the few questions over here. I think I have about 30-40 minutes, so I will do some questions towards the end. If I'm running out of time, I will jump towards the back. That is where the difficult question comes in, right? But in any case, we have stopped until question 5, I believe. So let's do question 5 first. Let's start with question 5. So what does question 5 says? So question 5 is this system, right? So this picture here, I have a network of capacitors. This is 6 micro, 3 micro, and 5 microfarad connected to a potential difference. After the charges reaches their final values, find the charge on C2 is, the final charge on C2 is 40 microcoulombs, and then find the remaining charges on the other capacitors, and also find the voltage. So firstly, let us solve the capacitor network system. Okay, so I have, this is question 5. Okay, so this is question 5, and then I have part A, terminal A. So this is 6 micro, and then this is 3 micro according to the question, and then I attach it to 5 micro, right? And then go to terminal B. Okay, so this is a capacitor in parallel. So when I have a capacitor in parallel, I can replace this with a single 3 plus 6, so I got 9 micro, right? And then I attach this to 5 micro, right? Then this is in series. So in series, what I have here is in series, hang on a minute, the question is telling us what? So the question is telling us that the charge on C2 is 40 microfarad, right? So what we have here is, let's focus on this first, right? So this is capacitor C2. I have 40 microcoulomb over here. So on capacitor C2, right, the charge on C2 is 40 microcoulomb, and the capacitance of C2 is 3 microfarad. So from here, I can immediately calculate the potential difference. So therefore, the potential difference is, I can use Q equals to CV, right? So it's equals to Q2 over C2. So it's 40 micro over 3 micro. So this will give me 13.33 volts. So the potential difference across here is 13.33 volts, right? Then from here, I can get a charge, because this is also parallel. So this is also 13.33, right? So this is also yeah, so I'll just write in symbols. So V1 is V2 is both equals to 13.33. So from here, I can calculate the charge on capacitor 1. So capacitor 1 is just C1 times V1. So it is 6 microfarad times 13.33. So I will have 80 microcoulombs. Okay, so 80 microcoulombs. So I have found this is 80 microcoulombs on capacitor 1. right? Then so now here comes the trick. I think this is where it's slightly tricky if you're not familiar with the concept. So I have found C1 charge, I have found the C2 charge. How to use this information to get the charge on C3? What we do know is, okay, I can get the equivalent capacitance, right? So the equivalent capacitance of C1 and C2 is C equivalent is, this is parallel, so this is parallel, so it's just C1 plus C2, and we have found this to be 9 microfarad, right? So 9 microfarad, then the potential difference across this is 13.3 volts, right? Because parallel capacitance have the same potential difference, 13.3 volts. So from here I can get the equivalent charge, right, is equals to C equivalent times the potential difference. So it is 9 micro times 13.3. So this is equals to this times this, so this is 120 microcoulomb. So what I have found here is the equivalent charge is 120 microcoulomb. Okay, why do I want to find this charge here? I want to find this charge here, but this two capacitor is in series. So this is also going to be 120 microfarad, right? The reason is because capacitors in series have the same charge. Okay, so I mentioned before in the lecture, right? I draw the picture. I see the reason is because induce charge of this plate, and then induce the other plate, and then induce the next plate. So everyone in series have the same Q. So Q of charge 3 is the equivalent capacitance that we found here. So it's going to be 120 microcoulomb. So that will give us the answer. Okay, yeah, right, pretty straightforward. Okay, so this is page 7. This is page 8. Right. Then what do we need to find for the next part? The next part is asking, wait, did I press record? Did I press record? Yeah, I mean, oh, you mean where Tesla is from, is it? Yeah, I'm not. I also didn't know he is Serbian. That's interesting. Yeah, because Tesla is an unusual, it's a name that I seldom hear, so I'm not familiar what region he is from. So Tesla could be a Serbian name. So the last part is we want to find the voltage VAB. Okay, find the voltage VAB. Well, we have found the voltage from here to here is 13.33 volts. So I just want to find the voltage across this capacitor. Then the answer shall be the sum, right? So the next thing that we want to do is the potential difference. The potential difference across the capacitance 3 is V3 is Q equals to CV. So it's just Q3 over C3, right? So we have found the Q to be 120 micro. The capacitance is 5 micro. So the voltage is 24. Yeah, 24 volts. So therefore the potential difference across AB is VAB is equals to the V equivalent that we have found, and then the potential difference across number 3. So it's 13.3 plus 24, right? So the final answer is 37.33 volts. Okay, what time are we at now? So we are running kind of short of time. So before, just in case we don't have enough time, let me jump ahead to question 10. And then no, let's do 11. I think 11 might be the trickier one. So let's do question 11, right? And maybe question 11 and 12. And then extra time we will do the rest. Okay. Oh, yeah. Resident Evil. What's her name? Lady Dimitrescu, right? And the 3 vampire sisters. And the other 3 houses. Yeah, there's a bad guy named Heisenberg in Resident Evil. But it's nothing to do with your Heisenberg in modern physics. So let's do question 11. So question 11 is this circuit, right? I have a switch initially in position S1. So basically it's just telling us how we charge the capacitor, right? So after it's charged, the switch is now turned to this position and then uncharged. But the first 2 parts is find out the initial charge and the energy stored in the capacitor. So initially, right? So initially is basically I have a battery, right? Attached to the capacitor C1. Okay, so I want to find the initially the initial charge of the capacitor is just C1 times the voltage, right? So the voltage is 120 volts of the battery, so it's just 8 microcoulombs, a microfarad, times 120 volts. So the initial charge is 9.6 times 10 to the minus 4 coulombs. So this is the initial charge of the capacitor, right? So I will call this Q0 because later it will change, but for now let us calculate this. And then for part B, I want to find the energy. So the energy is, you can use any of the formulas for the capacitor energy. So I'll just use half CV square for capacitor 1. So I use the value for the capacitance 1, which is 8 micro, and then the voltage is 120 square, so you will get 0.0576 joules. So this is the initial energy of the system. Okay. Now let's look at part C. Okay. So what is the issue with part C? So for part C, right? For part C is I have 3 capacitors in series. So let me make things a bit more convenient by finding an equivalent capacitance first. So let me point out that C2, C3, and C4 are in series. So the equivalent capacitance is because that is the purpose of having equivalent capacitance, right? Instead of considering 3 capacitance, which is so confusing, we just replace it with 1, and that is equivalent. So I got 1 over C equivalent is equals to 1 over C2 plus 1 over C3 plus 1 over C4. Okay, so what we get here is every capacitance here is 1 microfarad, right? So I got the equivalent capacitance is just 3. No, flip this, I got 1 over 3 microfarad. So what is happening here is I move the capacitance 1 here, right? And then I attach this switch to C2, C3, and C4. This is equivalent to having 1 capacitor and then 1 equivalent capacitance is microfarad, right? Instead of using C2, C3, and C4, I just consider this. Okay, so I consider this system now. Okay, so this is where switch has been moved to S2. So when I move to S2, right, then this will be it will start to discharge a bit, right? So what is going to happen? Initially, my capacitance C1 is having Q0. Okay, so this is charged to Q0. So when charged to Q0, and then I connect the switch to the other side, the Q0 will spread out, right? So it will spread out. So Q0 will be distributed across the capacitance 1 and the equivalent capacitance. Okay, so this is discharging the capacitor, but some of the charge will move to over there, right? So then we solve the same problem. I'm sure everyone is okay with this, because this is the similar thing that what you did to in the quiz, and most of you got it correct, right? That instead of touching the two metal sphere, I'm just connecting two capacitors. The idea is the same, am I right? So what I'm trying to say is, by conservation of charges, it will be spread to charge 1 and then the equivalent capacitance of charge over here, right? So this is my first equation. And then when in equilibrium, means after all the charges stop moving, then the potential on capacitor 1 is the potential on capacitor 2, equivalent capacitor, right? So what is potential 1? Using the capacitor formula, is Q over C1, and then this is Q equivalent over C equivalent, right? So I have the second equation, C1 over C equivalent of charge equivalent. C1 is 8 microfarad, C equivalent is 1/3 microfarad. So I have the equation that says that Q1 is equals to 24 Q equivalent. So this is equation 2, right? So I have two equations and two unknowns. So I can solve Q1 and Q equivalent by this over here. So I can substitute equation 2 into 1, so that my Q naught is equals to 24 Q plus Q. So you get 25 Q equivalent. So Q equivalent is 1 over 25 Q naught. So it's 1 over 25 plus my original charge, which was 9.6 times 10 to the minus 4. So my Q equivalent turns out to be 3.84 times 10 to the minus 5 coulomb. And then finally I can get the Q1 as well, which is just 24 times Q equivalent, and it is 9.216 times 10 to the minus 4 coulombs. Okay, so this is how we get the final charge of the system. Okay, so yeah, so we have found the final charges. And once we have found the final charges, well, Q equivalent, right? But what is the charges on C1, C2, C3? Right, so what is the charges on C1, C2, C3? It is the same, because capacitors in series have the same charge. So in other words, the charge on capacitor 2 will be in series with capacitor 3, in series with capacitor 4. And it will be the same equivalent charge on the equivalent capacitor. Okay, so the answer is everyone has 3.84 times 10 to the minus 5. This is 5. And Q1 has this. Okay, so everybody share, 2, 3, and 4 share the same charge. Q1 will be a different charge. And it's kind of expected because C1 has a different capacitance from the other 3. And then finally, for the last part, we just want to find the energy. So you just use the equivalent capacitance again. And this is 0.0553 joules. Okay, so if you compare to the previous number, the previous energy was 0.576. It has been reduced 0.553, right? And this is kind of what we expect, because if all the charges are in the same capacitor, everyone is very nearby, so the potential energy is higher, right? So if you remember Coulomb's law, if all the charge in the near region, the energy is higher. But if you spread out across different capacitor, you can lower your potential energy because your charges are further apart compared to previously. Okay, so yeah, so that is that was question 11. Okay. Yeah, I also didn't buy Resident Evil, but I've been watching people play on YouTube, so that's how I know all these things. Oh yes, yeah, the mod community. I saw the fly swat thing also. The V will distribute until correct, yes, that is why I mentioned the hint. Yeah, so my hint works, right? Everyone, I think almost everyone know how to solve it correctly, I believe. I haven't marked everyone's yet, but from what I saw, the few that I saw is mostly correct. Yeah, so the V will be the same, right? So if you connect conductors together, right? Yeah, that is the hint. Whether it's a sphere or a capacitor, if you connect conductors together, they will become the same potential, right? So when we were talking about the sphere, right? The sphere has radius 1, and then sphere has radius 2. So we can calculate the potential on the surface, right? So V2 is just the Q2 over 4 pi epsilon, and then radius 2, and then V1 is the same thing. Because on the surface is a sphere, right? So you use the spherically symmetric formula. So V1 equals to V2 kind of thing. Okay, so yeah, any other question? Not to say, yeah, voltage meter, yeah, in a sense about the potential difference, right? Yes. Yeah, so whether it's a sphere, in the ideal case, potential difference means what you do across the two terminals. Yeah. So that is our assumption that we have here. So when we did this, right? So the potential difference is the same. There is no, if I say this, right? That means I'm connecting the terminals, right? So I have the terminal A here is the same voltage as terminal A here, and then terminal B here is the same voltage as terminal B here, right? So this is an ideal wire, and ideal wire has no potential difference, so the potential here will be the same potential here. The terminal here will be the same potential terminal here, so therefore the potential difference will be the same, right? So this is what we call V1, and this is V equivalent. Okay. Yeah, so that is the reason why. Okay, any other question? Yeah, so ideal voltmeter. You know, speaking of Resident Evil, right? There is a physics video that they calculate that because the vampire lady is very tall, right? Then someone calculate what is the pressure and the force exerted if she step on you. So that is a very funny and interesting video, but also make use of all the physics stuff that we have been learning. The weight equals to mg, blah blah blah, and then but pressure, right? Pressure is force per area, so it depends on the surface area of contact, that kind of thing. I think it's by Nerdist, the Carl Green or something, the guy with the long hair. Yeah, he went to do the calculation. So yeah, question 12. Yeah, high heel. Yeah, so he actually considered high heels with a small surface area, and then the force is even higher. The pressure is higher, force per unit area. Question 12. Question 12 is, I think this will be the tricky problem, right? We have two square conducting plates separated by distance d, and then the k is given by these dimensions. Firstly is I want to find the capacitance of the system. That one is still easy, but later I want to find the capacitor if the V is constant, and then for the next part if the charge is constant. So what is going to happen? right? So let us try to figure out this problem. So let me try my best to draw a capacitor in 3 dimensions. So I have a plate, right? So I have a plate here, and then this is a parallel plate capacitor. Yeah, something like this. But I fill this with a dielectric medium until here. So this is my dielectric medium. So my dielectric medium is until this part, right? So so that means the capacitor on this side is slightly different capacitor on this side. So this part is still vacuum, this part is dielectric. We can treat this like a parallel capacitor. So the length here is L, right? This part is X, this part shall be L minus X, okay? So this is a vacuum capacitor, and then this part has a dielectric. So I can treat this as a capacitor in parallel. So this is C1, this is C2, okay? So C1, so this part will be having C1, this part will be having C2. So C1 is a vacuum capacitor. So vacuum capacitor is epsilon area over the distance, but the area now is L times this, so it's L minus X. The distance is big D, right? So D, and then the C2 is with dielectric. So with dielectric, I got a K here, and then epsilon, and then what's my area? The area is X times L, and then the distance is also D. Okay, so this is a capacitor in parallel, so I can find the equivalent capacitance. Which is just the sum of the two, right? So it's just C1 plus C2. So this plus this, right? So this plus this is, everybody got a factor of epsilon over D. So I got L square minus LX plus K LX. Am I right? Yeah, so I think I'm correct. So this is epsilon over D, and then this is L squared. LX with a K, so I got K minus 1 LX. So this is my equivalent capacitance. So I found the equivalent capacitance over here. Okay. That's too weird even for Final Destination. But okay, so here comes the tricky part. Now, let me raise up the question. What time are we at now? Okay, so yeah, there should be enough time to at least do part B. Suppose I have a capacitor connected to a battery, so it maintains a constant potential difference. So the voltage is constant, but I move the dielectric slab an additional distance dx in between the plates. So this is what's happening here. Okay, so what is happening here is I have a V constant, right? And then I want to see what happens to my energy. So firstly, I have V constant, and then the energy is given by U, right? So energy is given by U is equal to half CV square. So according to the question given, I'm connected to the battery. This term is constant. Okay, so this term is constant, but this C is given by this expression over here, which we have found. So what I have here is V squared over 2, and then I got epsilon over D, and then L squared plus K minus 1 Lx. Okay, so this is a function of X, right? So my energy is depends on X. This V is a constant, epsilon constant, D is constant, fine. So so U is a function of X, which means to say that changing X will cause a change in U. So changing X, changing U means what we can do is we can differentiate du dx. Am I right? Right, so du dx. So du dx, everybody here in front is a constant, so I got V squared epsilon 2D, and then differentiate everything here. So L squared is also a constant, differentiate X, I got K minus 1 L. So what I have here is I got k minus 1, and then I got epsilon, and then I got L, I got V square, and I'm dividing by 2D. Okay, so this is my du dx. So therefore, my change in this is equals to k minus 1 epsilon L V square over D dx. Right, so that is the answer that we are looking for. Right, so if I change by an amount of dx, my energy stored in the system will change by this amount. Okay. Yeah, does it seem like a very dirty trick to you? Right, it's just doing du dx, right? So once you have found this, du dx, that's all. Okay, so that is part B, is where V is constant. But right now, in the next part, right, my capacitor is in the case where I am disconnected from battery. So for this problem, V is not constant anymore, but the Q is constant. Okay, so how do we solve this? Okay, so if V is not constant and Q is constant, so let's deal with this, right? So we are still talking about the energy, but since we mentioned Q, right, so we need to put Q inside. So let's put Q. We use the formula involving Q, so Q over 2C. Okay, so right now we are going to see how it depends on time as well. So this time, this term is a constant, but C is not a constant, right? Because we have found C is a function of X, so it depends on X. So now in this case, we can see how it changes. So I just differentiate U with respect to X. Then I just differentiate this, right? So if I differentiate this, what I get? Q is a constant. So Q squared over 2 is a constant, but I differentiate 1 over C. So 1 over C, this becomes 1 over C squared, and then I use the chain rule. Right? So what I have here is minus Q squared over 2C squared dC dx. Okay? Then what is Q squared over 2C? So Q squared over C squared is actually equals to V squared, right? So if you remember the formula, Q is equal to CV, so therefore Q over C is equal to the voltage. So this is the voltage square of your capacitor. So so let us work this out. So du dx is equals to minus V squared over 2, and then dC dx. So dC dx means I differentiate the capacitance. What was my capacitance? My capacitance was all this over here. So it's differentiating epsilon over D L square plus K minus 1 Lx. So these are constants. So if I differentiate, I got V squared over 2 epsilon over D, and then I got K minus 1 L. Differentiate X, it will be gone. So du dx is equals to negative K minus 1 epsilon L V squared over 2. So the change in energy, if I move the slab inside, is just looks like the same answer as before, but with a negative sign. Okay, so it's the negative of the previous answer, right? What we got here was this, right? So negative. Part B. Okay, so then very quickly, right, to the last part. I know we're almost out of time already. So we use the formula du dx. I can actually determine the direction of the force. So if V is constant, then we have found du dx to be minus of du dx. So minus of du dx is if part A, right, du dx that we found is, so it's a minus of this. So it's k minus 1 epsilon lv squared over d. So this is a negative, right? Hang on a second. So F is equals to minus du. So I want to find the force, right? So so F is negative. So the force is downwards. Then if Q is constant, then I calculate the force du dx. I will get a positive number over here. Then F is positive. Force is upwards. Okay, so depends on whether you're attached to a battery or is disconnected to a battery. The capacitor is actually exerting an attractive or repulsive force onto the dielectric. So yeah, so that is the main part. Okay, yeah, so I don't know if I went too fast. We are a bit rushing off time, but if you are still not clear, I can explain more in the next class. So, but besides that, does anyone have any other question? Otherwise, that should be all for today. So we can stop the recording.